Wait, this is impossible. We only have the vertex 9 minus 14. To find A, B, and C, don't we need 3 points?
On the SAT, if they ask for the sum of coefficients, there's always a shortcut.
Look at the standard form. What happens if we evaluate the function at x equals 1? If x is 1, then x squared and x both just become 1.
Exactly. A times 1 squared is just a, and b times 1 is just b.
So the sum a plus b plus c is simply the value of the function at x equals 1. The sum of coefficients is simply the function evaluated at x equals 1. We can find this value using the vertex form of our parabola. Given the vertex is 9, negative 14, let's substitute those coordinates into the formula. Now we plug in x equals 1 to find the specific value of the sum. This simplifies to 64a minus 14. We just need to determine the sign of a to finish. We know the parabola has two x-intercepts. Let's look at what that implies. If a were negative, the parabola would open down and never cross the x-axis. But since there are two intercepts, the parabola must open upwards. This confirms that the leading coefficient, a, is positive. Visually, the sum of coefficients is represented by the y-coordinate at x equals 1. We've expressed the sum of the numbers as 64a minus 14. Since the problem states a is a positive constant, 64 times a must also be positive.
So the sum is effectively a positive value minus 14.
This means the total sum must be strictly greater than negative 14.
Now look at the choices. We need a value greater than negative 14.
Options A and B are both less than negative 14, so they're out.
Choice C is exactly negative 14. Can that be the sum?
Remember, a is strictly positive, so the sum must be greater than negative 14. That leaves only negative 12. It's the only value on the list greater than negative 14.
Brilliant! You solved a complex SAT problem using pure logic.